Okay, so now it's 1:30, so let's start. Okay, so the speaker is Professor Xin Zhou from Cornell University, and he will talk about minimal and CMC hypersurfaces. Let's welcome.
Thanks for the introduction, and I very much appreciate the opportunity to present this talk here at CBS 2024. This is the outline of my talk. I'll start with a brief introduction and go through something old, and then go to talk about something new regarding the existence of minimal and CMC surfaces in different categories. Let's start with the introduction. We all know that minimal and CMC surfaces are in equilibrium position with respect to the area or under volume constraint. They are physical and appear naturally in applied science. I take a few pictures online. The first one is soap film, which models minimal surfaces. The second one is soap bubbles, which models CMC surfaces. This one is a black hole, which we saw by Witten's talk. The boundary can also be modeled by either of them. The last one was an interesting picture I took from one of this Winter Olympic. The surf are modeled by minimal surfaces. Well, another important motivation we're interested in minimal CMC surfaces are the applications in other problems in mathematics, particularly in geometry and physics. For instance, the celebrated resolution by Shen Yao of the positive map theorem in general relativity. We listened Rick's talk yesterday, which applied theory of minimal surfaces, and the resolution of sphere theorem. The homeomorphic version in Riemannian geometry by Mika and Moore use the minimal surfaces. And the study of center mass in GR were initiated by Husk and Yao and then by others using formulations by CMC surfaces. And the work of Witten Yao and Yao on the boundary effect in string theory and GR also used CMC surfaces. And recently, the resolution of the Wilmore conjecture in surface theory by Marquez Nevis used minimal surfaces. So there are important tools in addition to their natural appearance in both mathematics and physics. Let me just put in this basic definition using first iteration. This concept will appear again and again in the talk. We model the surface by a line, and we deform the surface by certain vector field x. So we deform the surface to a one-parameter family of surfaces. If we take the first derivative of the area with respect to t, we know that equals the integral of the mean curvature times the normal velocity of the vector field. In that regard, the mean curvature can be viewed as the L2 gradient of the area functional. The surface is minimal if and only if the first variation vanishes for any compact supported vector field, which is equivalent to say that the mean curvature vanishes. And the surface has constant mean curvature if and only if the first variation vanishes for all volume preserving vector fields. This condition here is this volume preserving condition that implies the mean curvature equals to the constant. These will be my formal definition of these two concepts. Well, in this talk, I will try to explain to you a lot of connections. I'll put this photo again at the end. I'll try to bring in connections between the two problems under several different categories. The very early plateau problem, homological minimizing problem, the general existence problem, existence of multiple solutions, and existence of solutions with bounded topology. I'm not going to say too much because I haven't said anything about that yet, but at the end, I'll go to give you a tour of what I put in this picture. Let me start with the first one, the plateaus problem, maybe one of the earliest problem concerning the existence of such type of surfaces. Let's start with the minimal surface part of the plateau problem. In the 1760s, Lagrange raised the famous problem of finding a surface with a given boundary which minimizes the area. This problem was later named under Plateau, who did physical experiments using wires and soap films. So mathematically, I put the formulation over here. We put a simple closed curve in our space, and we want to find the map V from the disk into the space so that the boundary is a monotone parameterization of gamma such that V minimizes area among all such maps. This problem was solved in the 1930s independently by Douglas and Rado. They solved this by minimizing the Dirichlet energy I wrote over here. Grad U, you can grad V, you can treat V as a vector valued function. Grad V is the Euler gradient of each of the components. You take the square to calculate the L2 norm of the gradient. Later on, Mori systematically generalized this to Riemann manifold by changing R3 to any Riemann manifold. So that mainly concerns the regularity theory of elliptic PDEs. This is the classical plateau problem. This problem attracted a lot of attention, and after that, people tried to generalize this to higher dimensions and higher codimensions to prove, for instance, the existence of a minimizer, sigma n, spanning and given n minus one-dimensional boundary in Rn plus k. A lot of people, for instance, De George, Federer, Fleming, etc., developed the geometric measure theory, in particular the integral current theory, to show the existence of such a minimizer in the category of Lipschitz, or they call rectifiable currents. We have regularity theory in the codimension 1 case when k equal to 1. We know that by combining the work of De George, Federer, Fleming, Almgren, Simons, and others, area minimizing currents, codimension 1, area minimizing currents, is always given by a smoothly embedded hypersurface away from a single site of codimension 7. In particular, if n plus 1 is less equal than 7, the solution is always smoothly embedded. In higher codimensions, when k greater than 1, an area minimizer always has a single site of codimension less equal than greater equal than 2 by the deep works of Almgren and later on by Delales Sbordaro. So now let's move on to the more general setting, the CMC plateau problem. Everything is similar. You still have a wire in our space. This time, instead of spanning it by a surface with vanishing mean curvature, I want to span the boundary by a surface with some constant mean curvature, or prescribed mean curvature h. This problem were studied by Hinz and later on by Hildebrand. They consider this functional. You see the difference comparing with the Dirichlet energy. The leading term is still the Dirichlet energy, and they put a Lagrange multiplier term. This term actually, if you think of this as a surface, and you give a reference surface, say I fix this one as a reference surface. The second term more or less measures the volume in between this given surface and this reference surface. So that's the area subtracted by the volume times the prescribed number h. They prove that if h satisfies certain upper bounds, you always get a solution. This upper bound condition is very natural because if h is very large, you only expect to get a small bubble, as discussed in the morning talk, have a small bubble, so you wouldn't be able to get something with boundary. So later on, Brizis, Cohon, Zhou, and others studied the Rayleigh conjecture concerning the existence of more than one solution with a given boundary. Well, another problem we sometimes also call plateau problem concerns the existence of area minimizer within a homology class. So the minimal case is well known. So we consider an n-dimensional homology class, either with integer or mod 2 coefficients. If this homology class is non-trivial, we can use the integral current theory or geometric measure theory to obtain a minimizer in this homology class. And if the codimension is 1, this minimizer is smoothly embedded away from a codimension 7 singular site. And if in case greater than 1, it's smoothly embedded away from a codimension 2 singular site. So that is a pretty well-studied problem. And it's natural to ask what happens in the CMC category. Say, can I give a mean curvature H? Can I find an representative with constant mean curvature H? So the answer is still not very known. There are some partial results, but they don't have very satisfying progress yet. These are what I want to talk about, the plateau problem, either with a fixed boundary or within a homology class. And the feature is that we want to minimize the energy or the area. And then we want to talk about the general existence, which I mean, without assuming any topological restriction on the ambient manifold, can we still find interesting solutions of these two types of surfaces? I would like to start with the Armgren-Pitts min-max theory. The motivation was that previously we say that if the homology class is non-trivial, we can always find a minimal representative of that homology class so as to produce a closed minimal hypersurface. But what if I always assume the dimension is n+1 in the codimension 1 case. What if the homology is 0? Minimization doesn't help anything to find the closed minimal hypersurfaces. So this time we want to use a global min-max type variation theory to construct closed minimal hypersurfaces. So indeed, I see hypersurfaces, but there are some corresponding higher codimensional things that I chose to skip here. Let's look at this picture. The idea is as follows. So if I start with any hypersurface I minimize in its class, you can contract to a point. You get an empty site. You get a trivial solution. In order to find the non-trivial minimal surfaces, we actually take a one-parameter family of hypersurfaces, starting from a point. Then we enlarge. It's kind of like that. We're doing an X-ray scanning for this manifold. And every time we do X-ray scanning, we call this scanning a sweep out because it sweeps out the manifold. Every time we do such a scanning, we take the maximum area among this one parameter family. And then we take an infimum. There are several ways to interpret this number. One way to interpret is that this measures how wide the manifold is in order to cover it by a codimension 1 geometric object. And another way to interpret this is to use the classical mountain pass type construction for saddle points in calculus or nonlinear analysis. I also have a very intuitive way of understanding this idea. We can always imagine that the surface of the manifold has no friction, and each circle is a rubber band. It's a rubber band put on a surface with no friction. Always try to shrink its length. If you only have one rubber band, it will retract here or retract there. But I have one parameter family so that they're not allowing to all retract here or retracting the other way. So there's something non-trivial in between. Ideally, when each of the rubber band trying to minimize its length while keeping the altogether as a whole, eventually we achieve some stationary configuration like the one parameter family of the red curves. So the one with the largest area in this red family should be stationary for the area functional. And if they're smooth and if they're stationary, we know that by the first variation argument that the largest slice is the minimal surface. This is very intuitive, but mathematically there are so many deep analysis involving. But fortunately, from 1961, initially by Armgren and then by Pitts and Xin Zhou until 1981, we know that this has become a theorem. That the ways I defined before is always achieved by the area of some closed minimal hypersurfaces counted with integer multiplicities and up to a small singular size. So here I say integer multiplicities sort of as a linear combination of areas, but the coefficients are all integers. So the series is that once you can define such a number L, I mean, in my picture, I use a one parameter family, but later on I will show you multi-parameter families. As far as you were able to define such a number, you can realize a number as area of minimal surfaces. Then you may ask whether the number is positive. I say that's trivial by the isoparametric inequality. The reason is because we start with something that bounds zero volume. When you enlarge it, it starts to bound some volume. Because it's going all the way up to the other end, at some point, the hypersurface bounds half of the total volume. The isoparametric inequality, which we saw in the morning talk, tells us that the area also has a lower bound, strict lower bound, depending only on the ambient geometry. So that tells us that the number I define is always non-trivial. And combining together, the corollary is that every closed manifold admits a closed minimal hypersurface up to a small singular size. If the ambient dimension is equal than 7, they're always smoothly embedded closed minimal hypersurface. So then let's move on to the world of CMC surfaces. The first thing I want to talk about are isoparametric CMCs. We saw the isoparametric inequality this morning. Let me go a bit further. Now I fix a closed manifold of dimension n plus 1. So this time I want to produce a closed CMC hypersurfaces. So we can always do that by the isoparametric problem. Namely, suppose V is a positive number less than the total volume. Then I consider all domain with this volume and I minimize this parameter or the boundary area. This is a classical isoparametric problem. By geometric measure theory, integral current theory, the infimum is always achieved by some omega naught, a particular domain, which bounds half of the volume. And we also know that its boundary is smoothly embedded away from a codimension 7 singular set. The regularity is the same as before in this sense. And it has constant mean curvature because it is volume preserving minimizer. Under this volume constraint, this guy is the absolute minimizer. I showed that. Under volume constraint, if it's stationary, it has constant mean curvature. Okay, this story sounds to be pretty satisfying because we can always solve the existence problem of CMCs. But we actually have no control over the value of this mean curvature. We can control this volume. Indeed, for what volume number you give, you can produce a CMC bounding that volume. I'll go back to a point later. But you cannot control the mean curvature. Well, if you compare this with the minimal surface part, in the minimal surface case, particularly the min-max theory, we want to find surfaces with prescribed zero mean curvature. In that regard, if you want to generalize, you want to show that given any mean curvature, you want to find the surface with that given mean curvature. Well, I say this is also interesting. I'm not saying this is not interesting. This is a different part. I'll go back to this part later. Okay. Yeah, a couple years ago, with Jonathan Zhou, we investigated this problem. We want to find a closed constant mean curvature hypersurface with prescribed curvature in an arbitrary closed manifold. We generalized the Almgren-Peace min-max theory to the CMC setting. We were able to prove the following. Well, I proved this for lower dimensions, I mean, just to get smooth solutions, but it has been generalized to higher dimensions by others. So given any closed manifold, Riemann manifold of dimension between 3 and 7, for any prescribed number C, positive, there always exists a smooth, closed, so I call it almost embedded, hypersurface of that given mean curvature C. So you can construct a closed hypersurface, CMC hypersurface, with any given mean curvature C. I mean, we proved this for positive mean curvature. If you want to get something with negative mean curvature, you can flip your orientation. You get negative mean curvature. So here, almost embedded, which means that the surface can be immersed but they cannot go across each other. They only touch. Some people call this is strongly Alexandrov embedded. This is natural in a CMC setting. Another interesting feature or remark related to the theorem was we can regard this as a higher dimensional version of one of Arnold's conjecture on the existence of closed constant geodesic curvature curves. So Arnold, from a dynamical system point of view or symplectic geometry point of view, were interested in the movement of electronic particle inside electronic field, magnetic field. Sorry, the magnetic field can be written as some number c times the metric tensor that models some magnetic field. A particle moving in such a magnetic field goes through some so-called magnetic geodesics. Magnetic geodesics are nothing fancy but a curve with constant geodesic curvature. Well, this conjecture is still open, but we were able to solve a higher dimensional version of that. Well, if you compare the Almgren-Peace theorem with geodesics, that's kind of different. Almgren-Peace was motivated by the existence of closed geodesics on surfaces. I'll also go back to this later. My talk will be closely related to the method, so let me talk a little bit about what we studied. We studied the weighted area functional, sort of in the same spirit as Hildebrand functional I mentioned before. That is a mapping problem, and this is more like an intrinsic functional. So the idea is that, so if this is a manifold, we consider a domain. So this is omega. We consider not only the area of the boundary, but also the enclosed volume multiplied with a constant c. You can treat this as the Lagrangian multiplier of the area functional as the same spirit. Xin Zhou, Hildebrand. Well, if we take the first variation I did before, the area functional always gives the mean curvature. And the volume part gives nothing but the normal speed along the surface. So grouping them together, you get that the first variation of this new functional is h minus c times the normal speed of an arbitrary vector field. As I mentioned before, if you only consider volume preserving variations, the second integration is 0. So you leave h to be any constant. Well, this time, if you consider this functional, but allowing arbitrary vector field x, vanishing of this first variation implies that h has to be the same, identical equal to c. So that is the advantage of using this functional rather than doing an isoperimetric variation. It's easy to see that we cannot produce a non-trivial CMC surfaces by minimizing this functional because well, omega is a domain. If I put the argument as a total manifold, this part will be 0 because the boundary is empty. Well, the second negative part achieves its maximum. So the functional is always bounded from below by the AC functional of the total manifold, which equal to b minus c times the total volume. Yeah, you cannot directly obtain minimizer. So natural things to do is to do the min-max as Almgren-Peace. So I sort of motivated using curves, and this is sort of the same setup. I also need to go back to this concept. So let me just say a few words of that. We work on the space of sets with finite parameters, namely all subsets of M whose boundary has a finite n-dimensional Hausdorff measure. It can be very irregular, but we require it has finite parameter. So this type of sets has been studied by Cacciapoli many years ago, and Cacciapoli were able to show that this condition implies that the boundary away from a small set is rectifiable. It has a Lipschitz structure. This is very nice set. And also it's easy to see that this set is contractible. Given any Morse function, you can use in the level set to push everything to empty set. It's contractible set. I just reformulate Almgren-Peace. Last time I consider a one parameter family of hypersurfaces. This time I consider a one parameter family of sets. And I start with the empty set and ended at the total manifold. And it's easy to see that there's only one such free homotopy class connecting empty set to the total manifold because the whole manifold is contractible. Every two such loops are homotopic to each other. And then we can define the min-max similarly as Armstrong piece. So each time along each sweep out, I take the maximum AC, and then I take the infimum among all such one parameter families. Again, by the isoparametric argument is positive. It's not that trivial, but it's not that hard. Last time I find a surface which bounds half of the volume, or divide the manifold into two equal parts. This time you can find a set which bounds a very small volume, because in the small volume case, so this part dominates that part, so you still get some strict positivity of that. And Jonathan and I mainly prove that this min-max number is achieved by the AC some almost embedded boundaries with constant mean curvature C. So we build up this regularity theory in our early paper, and in a later paper, we check that it's achieved. These are about the general existence. Let me summarize that in any closed manifold, we are able to find the closed minimal hypersurface by Armstrong piece, and we're also able to find the closed CMC surface of any prescribed mean curvature by my work with Jonathan. And we were also able to find the closed CMC surfaces bounding any given volume. I think let me try to go into my photo in the beginning, and let me help you to compare what we know. I mainly discussed this line. So in the h equal to 0 category, using Armstrong piece, we can always find existence of closed minimal hypersurface. And if you want to find CMC with prescribed volume, you can use isoparametric idea. And if you want to find CMC with prescribed mean curvature, you can apply my work with Jonathan. So that's about this. Yeah, I'm going to talk a bit about that in the next part. So I'm going to then talk about what do we know about topology, maybe. So yeah, and other questions? So this part, I want to talk about surfaces with control topology. What can we do even in dimension 3? Do we have more information? A famous conjecture was a conjecture of Yao made in his project. We call it Yao's false minimal spheres conjecture. I'm always starting with minimal, then I shift to the CMC part. The conjecture asserts that there are always 4 distinct embedded minimal 2 spheres in any Riemann manifold diffeomorphic to S3. Let me motivate the conjecture. I say this is a 3-dimensional analog of Poincaré's conjecture on the existence of 3 simple closed geodesics on S2. That is a famous problem. We sometimes call the Luft-Chernik-Schneermann theorem, which was pioneered by their novel ideas. That is the first motivation, because in 2 dimensions, you expect to have 3 simple closed geodesics. So in 3 dimensions, you expect to have 4. And the actual reason was due to the Smith's conjecture, which implies that if you consider all embedded S2 in S3, endowed with a smooth topology, that deformation retract to the space of grid spheres. We know that a grid sphere is uniquely determined by the antipodal points that is homeomorphic to RP3. So a Morse function on RP3 always has at least 4 critical points. So you expect to have 4 critical points of the area functional, which would be smooth embedded minimal 2 spheres. Another motivation was the Sachs-Uhlenbeck theory, who proved that in any n-dimensional sphere, when n greater than 2 always contains at least 1 branch immersed minimal 2 spheres. So back to that time, we know the existence of solutions which may not be as regular as the conjecture expected. But we also have the Armstrong-Piss-Simon theory, which tells us that when you apply to S3, you always get at least 1 closely embedded minimal surface, even we don't know the topology yet. So combining all, I think it was very tempting to make this conjecture. Let me go through what was known about this conjecture. Shortly after the conjecture was made, Simon Smith, Leon, and his students proved that there is at least one smooth embedded minimal two-sphere. Actually, this was not published in a journal, but was only in ANU's thesis library. What's the difference between Armgren Peace and Simon Smith? Armgren Peace theory uses heavily GMT, geometric measure theory, and the relations between surfaces are homological. If you think of surfaces which are equivalent in the homological sense, the surfaces can have different topology. So you wouldn't expect to get a solution with fixed topology, even in dimension 3. You have to restrict your variational space. A general principle in variational theory was that the larger your variational space is, the easier the problem would be. Well, the smaller space you had, the harder the problem would be. You imagine this would be harder than that, even though have the same spirit. They indeed combined the Armgren Peace idea with earlier work of Armgren Simon and Ming Simon Yao on isotopic minimizing problems. The isotopic minimizing problem concerns that you start with the surface and deform it only along by ambient diffeomorphisms. And you minimize among that class. That will be way smaller than deforming the surface of any topological type. But they were able to show the existence of a minimizer with fixed topology. So that's why Simon Smith were able to do that in the min-max category. These results were later generalized by others. For instance, Coden Deleuze and many other people, they were able to show that every remaining three manifold contains a close embedded minimal surface with genus bounded from above by the Higard genus. And in special cases, they were able to show that was the Higard genus. So let's go back to Yao's conjecture. This is an outline of the progress. Well, due to limited time, maybe let me just read this part. Okay, so Brownwhite did some earlier contribution to that, and he was also able to show that 4 was a sharp number, because he showed this under this specific metric. This is a conformal change of the round metric, and the conformal factors given by the polynomial with coefficients satisfying these conditions. He showed that there were only 4 embedded minimal two spheres given by the cut of the 4 planes in R3, R4 with this sphere. So last year, my collaborator and I generalized the earlier works, and we were able to show that if the metric is generic, or if the metric has Porto-Ricci curvature, the conjecture is true. There are at least 4 embedded minimal two spheres. I mean, after Simon Smith, we actually all know what to do, what to apply using the theory. But the major challenge was the so-called multiplicities. I'm not going to show you, but you can imagine that the space of two spheres has rich topology, which is RP3. So you can have higher homotopy class to apply the min-max theory. But the theory intrinsically carries integer multiplicities, which means that if I apply the second time, I may get the first solution counted with higher multiplicities. And the previous works try to do that, overcome that by hand. And we were able to prove a multiplicity one-type theorem that gives this, but only under Bumphill-Ricci-Porte assumptions. This multiplicity one theorem has been applied by 4 of my students and a former postdoc. They were able to show that the existence of other minimal surfaces with control topology in length spaces. I mean, they proved a number of results. I list a lot, but let me only emphasize the first one. In RP3, the real projective space with Porto-Ricci curvature, they can construct at least 4 embedded minimal projective plane and at least 4 embedded minimal tori. And if the matrix is generic, there are at least 5 minimal embedded tori. The difference was that you can imagine in S3, every surface is separable. It separates the manifold into 2 parts. But in RP3, if you work with the projective plane, this is non-separable. Actually, my technique doesn't directly work over there. So what they did is to treat this as S3 with Z2 action. they did everything equivariantly. They were able to reproduce equivariant version of the multi-prevent theorem and get that. There are definitely other interesting works ongoing, but I want to move on to talk about what we know about CMC surfaces with control topology. Again, first we are interested in CMC two spheres as an analog of Yau's conjecture. Rosenberg-Smith, this is a different Smith. In 2010, they made such a conjecture. They conjecture that every remaining three sphere, S3 endowed with the Riemann metric of positive curvature. They actually didn't specify which positive curvature they want, but let's pick whatever your favorite positive curvature. Admits an embedded two sphere of constant mean curvature C for every C positive. This can be viewed as a combined generalization of Yau's conjecture, Yau's four-sphere conjecture, and Arnold's conjecture. I explained both to you. So Arnold concerns closed curves of constant geodesic curvature, and Yau conjecture concerns S2 with zero mean curvature. And this is a combined generalization of that. However, shortly after, Torobo showed that for some particular C and in certain particular Bergier spheres, all immersed CMC2 spheres of this mean curvature C have to have self-intersections, which means that there doesn't exist any embedded CMC2 spheres for some mean curvature C. Well, it's a little bit counterintuitive, but anyway, these Bergier spheres are very symmetric, and Rosenberg earlier proved that all CMCs are also symmetric, so they can reduce everything to ODE. You can calculate, classify the solutions. So I think a modified or amended conjecture was that every remaining three sphere of positive curvature, let's say positive Ricci, admits an immersed two sphere of constant mean curvature C for every C. This doesn't have any contradiction with Torobo's examples. To construct immersed CMCs, there were some earlier work, some histories using variational idea. A natural way is to using the mapping method pioneered by Xin Zhou. So they deal with boundary problems, and Struer were able to generalize their work to the closed case. I mean, a couple years ago, Darwin Chen and I proved the following two theorems. We show that every remaining three sphere with non-active Ricci curvature admits at least one branch immersed to sphere of constant mean curvature C for every C positive. I mean, we more or less solve the conjecture modulo the possible existence of branch points. And we were our method also applied to a general metric. We show that for a given arbitrary metric for any C, there exists I mean, for almost all C or for generic C, you can produce the immersed two sphere of that constant mean curvature C. And then you may ask, what happens if I'm going to use this generic C to approximate the arbitrary C? So the missing part is that the area of them may diverge. You may convert to a complete one. I mean, we haven't done too much in that direction yet. I'm not sure whether it's possible. If we were able to show that all these CMCs have bounded area, obviously you can fill all the spectrum. So an interesting question left over as compared with the Simon-Smith theory was that I mean, instead of discussing three sphere, let's consider arbitrary closed Riemann manifold. Can we always find closed CMC surfaces with both controlled genus and given mean curvature? Say, applies when the pi3 is non-trivial. I mean, in our spherical manifolds, we are not sure if it's non-spherical, so our method applied. At least pi3 is non-trivial. I mean, it's tempting to conjecture that every closed manifold admits a branched CMC immersion of curvature C and genus bounded by the Higard genus. So there's a natural sweep out, there's a natural functional to apply. The things is whether one were able to build up the existing regularity theory there. So this is the fourth part of my talk. Any questions? So in this part, I surveyed the existence of minimal surfaces with controlled genus in 3-manifold, and also the existence of CMC surfaces with controlled genus in 3-manifold. I mean, here I want to say that I never talk about the isoperimetric problem, because if you do isoperimetric, in general, you don't have a topological control, so I just skip that part. No, I do min-max. Yeah. I want to know that they are uniformly bounded. If they are, then my second theorem we're able to generalize to all C instead of almost all C. This problem were studied by Meeks and his collaborators in homogeneous manifold. They were also trying to show that there doesn't exist complete CMC surfaces with arbitrarily large area. They try to rule that out, but I'm not quite sure in the range setting. And also in arbitrary manifold, their manifold were homogeneous. In the last part of the talk, I want to talk about existence of infinite many solutions. I'm going to really tell you something new that happened in the past couple of months. Again, I'm going to talk about both the minimal world and the CMC world. In the minimal world, there was the famous conjecture of Yao. I mean, this is problem 88, and the previous one was 89 in the problem list. The conjecture says that any 3-manifold must contain an infinite number of immersed minimal surfaces. Again, the motivations are parallel to the previous motivations, because Poincaré in his paper 1905 raised two questions. One was whether you can find existence of infinite many closed geodesics on closed surfaces. The other was whether you can find at least 3 simple closed geodesics on surfaces. Well, this problem may sound easy, but was not solved until the 1990s. The other one was solved until 1989. I think this is one of the motivations. This is a directly one-dimensional higher generalization of this conjecture. And also another one was the Armstrong-Piston-Simon theory I mentioned before. You at least have a very effective tool to produce at least one closed minimal surface in this manifold. Well, I mean, in short, this has been solved. I'm going to show you these answers in a couple of slides, but I first want to go through some major ideas behind the proof of that. This is the volume spectrum. Recall that I introduced this concept before when I talk about the CMCs. This is the space of size with finite parameter. This is the space of all subsets of the manifold whose boundary has finite area. I say that this space has very natural topology, it's contractible. It's very simple space. However, Armstrong in his very early paper in 1961 observed the following. If I only consider this space, it's a contractible space. We won't expect to get interesting variational theory there. We want to see topology, non-trivial topology. The theorem says that, I just formulate a little bit differently, but in short, there's a natural Z2 action over this space. The Z2 action flips the inside to outside. I mean, this space, this is omega, this is its complement. There's a Z2 action of flipping one to the other. If you model the Z2 action, sometimes people call this multiple currents. I'm now call it Z2 boundaries. So every hypersurface is a boundary, but I put the Z2 coefficients to ignore the orientation. So this is hypersurfaces under this equivalent relations is vaguely homotopic to RP infinity. This was not very surprising nowadays, because you can imagine this contractible space as R infinity, and you have Z2 action sort of to get this RP infinity. Or this is S infinity, this is RP infinity, this is such analog. So once we have this result, we must get very exciting, because we have very fruitful topology. For instance, the Z2 cohomological ring is a polynomial ring with a single generator. Several years later, Gromov observed the following. He observed analog between these and the Laplacian eigenvalues. So in Laplacian eigenvalues, we also have a min-max definition, and I'm now going to directly show the corresponding one in this world. Because the original space is vaguely homotopic to RP infinity, we want to show what are the RPK inside that. What are these finite dimensional real projective structures inside this huge space? The definition uses algebraic topology. So consider, for instance, a k-parameter family of hypersurfaces. The parameter space is X, k-parameter family. Now, so there's a single generator in the cohomological ring which takes its piece power and put it back. If this is non-trivial in the cohomological group, we call that is a piece-weight pod. This is analog of RPK inside RP infinity. Roughly speaking, there's a geometric way of describing that. Suppose that given any p points inside the manifold, if I were able to identify a particular parameter so that the hypersurface contains all of the p points, I call this like a k-parameter family, a p-parameter family of piece-weight pod. You may ask whether you can find that. In particular, I have no restriction on the topology of this hypersurface. I can pick them to be parallel hypersurfaces. So at given a point, I pick a surface. So I'm always able to produce such non-trivial p-parameter families. Okay. So this is kind of RPK inside RP infinity. And then, so we can write out Gromov definition of the volume spectrum. So given a piece-weight pod, this is something which carries topology. You take the maximum area and then take the infimum. This appeared in my previous slides quite often. Interestingly, Gromov conjecture, which was confirmed by Lukumovich and Marquez-Neves, that this spectrum obeys an Weyl law. This Weyl law says that the asymptotic behavior depends only on the dimension and the volume. If you normalize the volume to be 1, they all have the same asymptotic behavior at the same dimension. And the power is 1 over n plus 1. It's a sublinear growth. And also, Marquez-Neves generalized the Almgren-Piston-Simons theory to this homological min-max setting. Previously, people only consider min-max under homotopy equivalence. And now we consider min-max under homological equivalence. This is a small improvement. They were able to show that each of the number is realized by the area of some closed minimal hypersurfaces counted with integer multiplicities. You can imagine this is a linear combination and the coefficients are integer. Another way to interpret this is that if you think omega p as the p's Laplacian eigenvalue, so in that eigenspace, you may have several eigenfunctions. Each of them have some multiplicities. I mean, these are all very heuristics. No. So let's go back to Yale's conjecture and see how we combine all the recipes to prove. So the conjecture suggests to find infinite many minimal surfaces. There were two major breakthroughs, first by Marquez-Neves and then by Antoine here. So we can combine the volume spectrum, which obeys the Weyl law, combine the min-max theorem, which give the existence, combines the Luchternik-Schneiderman theory, and the counting arguments. They first confirm that when Ricci curvature is positive. They were able to prove much more than the conjecture. So the theorem says that in any lower dimensional manifold with positive Ricci curvature, there always exists infinitely many closed embedded minimal hypersurfaces rather than merely emerged. And Antoine then later removed this assumption using his novel cylindrical type volume spectrum. And now, so his theorem fully confirmed this conjecture. So behind the proof, they have very clever way to going around the multiplicity, but I also want to say a few words because I have some work there. So multiplicity means that when you apply the min-max theory to omega p, you may construct something you already see previously, or the reoccurrence, right? Inspired by Uhlenbeck's generic simplicity theorem for Laplacian eigenvalues, which says that given a fixed closed manifold, for generic choice of the Riemannian metric, the Laplacian eigenspace is always simple. So each Laplacian eigenvalue has a one-dimensional eigenspace. The Marquez-Neves conjecture that in this world, for generic metric, the multiplicities should always be 1, which I confirmed a couple years ago. And this combined with Marquez-Nevis work on Morse index sort of give a very interesting Morse theory for the area functional. Indeed, in these dimensions for each integer p, there exists a closed minimal hypersurface whose area equal to the spectrum and whose Morse index is exactly given by p. So we can generically, we can not only produce infinite many solutions, but we can list them by their index. They later also find a local version of that. So you can consider a subset of the total manifold. You also can count or compare the existence of minimal hypersurfaces comparing with the topology. Any questions? So finally, I want to talk something new. What are the analogs in the CMC world? So there are two directions to push. As I talked in the beginning, one is the isoparametric idea, the other is prescribing the mean curvature idea. So let me first talk about the prescribed mean curvature idea. Regarding the existence of more than one CMCs with prescribed mean curvature, there was a conjecture by Arnold. Indeed, Arnold conjectured that on S2 with the arbitrary metric, there should exist at least two closed geodesics with constant geodesic curvature. So one-dimensional higher, you can imagine, it's tempting to conjecture that, so in these dimensions, there should exist at least two distinct, smooth, closed, almost embedded hypersurface of constant mean curvature C. I mean, which I call the twin bubble conjecture. I think it's very natural to us. Well, in the beginning, I mentioned that if you apply my work with Jonathan, starting from empty set to the total manifold, consider this path and apply the min-max, every such paths are homotopic to each other. You were only able to detect one critical point. I mean, you want to look from empty side to the whole manifold, but you also want to look from the other side. You cannot do that directly because they're all homotopic. So what you can do is to consider not only the AC of the omega, but also the AC of its complement in order to see from the other side. That's to say you take a maximum between these two functionals. That's a way to look this one parameter family from the other side. The technical point is that this functional is sort of only Lipschitz under the size which has half of the total volume. These functionals look like the absolute value of x. A function. It has a Lipschitz singularity there. This motivates us to consider something interesting. So which we call the whether you can produce multiple CMCs which includes a fixed volume. I mean, this is also analog of Yale's conjecture under this isoparametric category. In the beginning, I say that if you fix a volume, minimize the parameter, you get isoparametric CMC. They ask you, if I fix a volume, can I produce more than one CMCs with that given volume? This is a question. I mean, it's very surprisingly that this question and this challenge are sort of together. They're the same problem. With my postdoc, Mazurovich, we proved the following. At least now, from dimension 3 to 5, for generic metric, we were able to show the existence of like infinite many CMC hypersurfaces that includes half of the total volume. In one regard, it answers this question for half of the volume. In the other regard, it tells us that if you want to go around CMCs with including half of the volume, the problem may be very challenging. And in ongoing work, we almost finished. We have to polish and post it online. We are able to show that from dimension 3 to 7, for generic metric, for any number C, either there exists infinite many CMCs with this given mean curvature, or there exists infinite many half volume CMCs. So mean CM, we don't know the value of the mean curvature. You cannot. It could be 0. I mean, in this case, we were able to generically, they're not minimal. We don't want minimal to appear, but in general, it could. I mean, so now I want to tell you a story about that. We have some very interesting structure behind that. Again, I go back to the Cauchy-Polis as I mentioned before, sets of finite parameters. In this time, I only consider all the sites which include half of the volume. I call this the C1 half. This can be viewed as a hyperplane in the total space. I mean, the total space of all subsets, and now I restrict to all subsets with half of the volume. This is a hyperplane. It's again contractible. And if we prove that if you quotient by Z2, so this time these are the fixed points under the Z2 action, because when you flip, still bound half of the volume. It's fixed point. This is, we call it half volume Z2 hypersurfaces. This is also homotopic to RP infinity, vacuum homotopic to RP infinity. And then we can define a half volume spectrum that in the same way as Gromov defined for the volume spectrum. And last year we proved that they obey a well law, the same asymptotic constant, the same asymptotic behavior. It's not very hard because these spectrums sort of sit in between two nearby spectrums of the additional volume spectrum. Okay, so now we found some new spectrum and they have geometric meaning. So we searched for the existence theory. And this year, a couple weeks ago, we proved that at least from dimension 3 to 5, for generic choice of Riemannian metric, for each integer p, there exists a close embedded CMC. We actually don't know the mean curvature value, but we do know that they enclose half of the volume and its area equal to the volume, the half spectrum, half volume spectrum. This can be treated as a CMC analog of the multiplicative one theorem for minimal hypersurfaces, and it directly gives you as a corollary the existence of infinite many half volume CMCs. There are some interesting ideas behind. In particular, now we have a hyperplane, we have a subset of the Cartier polysets. We want to develop a variational theory there, but we found that we cannot directly use the idea of arm piece. The major challenge was that to preserve this half volume condition, you tend to use vector fields which are divergence free to deform them. But the divergence-free vector fields, even though they are linear, but they're not easy to be manipulated. Instead, I think this is the most interesting part. We consider sort of a Ginsburg-Landau type of panelization for, I mean, we were motivated by that for harmonic maps. We introduced the idea for this problem. We consider a panelized functional, that is the area of the hypersurface plus a panelized term. The panelized term is the total volume of the set minus half of the total volume, power times a large integer k. I mean, if you look for the harmonic map problem, you know that if you want to solve a harmonic function, it's easy. But you want to solve a harmonic map goes into a closed manifold, it's hard. So the panelization idea is you allow your map to go into the ambient space, but you added a term panelizing the distance from your map towards this embedded submanifold. If you let the coefficients to blow up, eventually you retract your solution to the manifold. This is a similar idea. I mean, we use this functional, so this time my hypersurface can be any boundary. We don't have to put the half volume constraint there, but the panelization eventually will let the volume go to the half volume. So that's the idea. I mean, when k goes to infinity, we expect that the critical points of these will convert to that of the area in the half volume space. However, the major challenge introduced here was that this is no longer an local functional in the sense that if I perturb a little bit, you have a global effect because of this term. So we have to develop some new ideas. So indeed, for this functional, we get interesting existence theory. We were able to show the existence of a critical point at the higher. I mean, to be short, the solution has some CMC parts and some minimal parts with multiplicities. I mean, these are not satisfying because even if what I said before works well, when k go to infinity, the limit could be a CMC plus some minimal bubbles. And the minimal bubbles can ruin the existence theory. Unfortunately, we were able to do another perturbation. I mean, this is much fancier than before. I added some Lagrange multiplier term together with this panelization terms. Even for this complicated functional, we will still be able to show the existence of critical points. So mean curvature is given by this function together with this derivative terms. This time, we were able to show that there's no minimal bubbles. Eventually, we'll only either converted to all minimal bubbles or convert to a non-trivial CMC. Generically, a minimal bubbles, which includes half of the volume, doesn't exist. So generically, we only obtain CMCs there. Yeah, so let me just give a remark to finish my talk. The dimension restriction will only use to show that when the panelization go to infinity, the mean curvature are bounded. Because if you look for this equation, this coefficient blows up. We need to show that this part is smaller. I mean, the multiple are uniformly bounded. So use some lower dimensional restriction there. But everything else, the existence and others works well in any dimensions. Okay, so I think this is what I taught. Let me just say, so this is the Yau's conjecture. We have very nice theory. If you do the prescribed mean curvature part, you have the twin bubble conjecture, which is open. And if you think about the isoparametric generalizations, and we do have an interesting recent work. So I think I stop here. Thank you very much.
Very much for the great talk. Okay, are there any questions or comments?
So, can you give some intuition about the dichotomy? Why do you have this dichotomy?
Yes, because we have very powerful theory. I mean, let me tell you about this using this theorem. So in this time, we can ignore this part and put this as, I say that is the absolute value of x. You can change absolute value of x to x squared plus epsilon squared square root. And then you can have existing theory. And then you let epsilon go to 0, they may have some dichotomy. Either the slope go to 1 or minus 1, or you stop somewhere. And that's sort of technical intuition of why that happens. Geometric intuition, yeah, I mean, geometric intuition is a little bit hard. Maybe I'll tell you afterward. I mean, if you really think about how to open up this RPK structure into SK structure, as far as you can ignore, you can bypass this half volume part, then you are okay. So Struve already have something similar in his book, but in his problem, his spectrum grows super linearly, so he will never see that half volume obstruction. But this is sublinearly, you may have such obstruction in between. Maybe I'll tell you more about the geometric part.
Any other questions or comments?
Sorry, this is probably a very ignorant question, but do you envision, do you think that it's possible to generalize some of the sweep out ideas to minimize areas of singular objects? For example, if you had, like, you're in dimensions where you have some graph, but yeah, it's.
I think the most natural things to conjecture is that, so in all the words I talk about here, we use Z or Z2 coefficients. I mean, under these coefficients, you literally only see smooth object. Now you can think about Z3 coefficients. Under these coefficients, you may see something with a triple junction. And if once you allow this object to come to geometry, I think you should expect to see single object at the end.
Thank you.
Other questions or comments?
We want to have a sharp theorem. We need that dimension restriction so to show that when K blows up, this multiple is uniformly bounded. Because if it's not uniformly bounded, then you're able to show that it converts a lot of small bubbles, and that will violate that the function of the total area is bounded. I mean, there was this the Docamo type uniqueness for CMCs we used to show that the limit behavior are small bubbles. I believe it can be removed in the near future.
Questions? So if not, let's thank the speaker again.
Thank you.